So we shall continue our discussion on Riemann series integral. So the next theorem is So it says assume that alpha increases monotonically and alpha dash belongs to R on closed interval a comma b. That is alpha is Riemann integrable on closed interval a comma b. Let f be bounded real valued function on closed interval a comma b. Then f belongs to R of alpha on closed interval a comma b if and only if f alpha dash belongs to R on closed interval a comma b. That is, we need to prove f is Riemann still a integral on closed interval a comma b if and only f alpha dash is Riemann integrable on closed interval a comma b. So in this case we write integration a to b f d alpha is equal to integration a to b f of x alpha dash of x dx. So we shall see the proof. So given that alpha dash belongs to R, given alpha dash belongs to R on closed interval a comma b, so using a Riemann criteria for integrability, we have given average 0, there exists a partition P is equal to say x0, x1 up to xn of closed interval a comma b such that up alpha dash minus lp alpha dash is less than epsilon. Now observe here I am writing with respect to alpha dash because I am applying Riemann criterion for alpha dash. And now what is UPF? UP alpha dash. It is nothing but summation mi into delta xi is equal to 1 to n, where what is mi? Mi is nothing but it is supremum of alpha dash of x, where x lies between xi minus 1 and xi, and lp alpha dash is nothing but summation I is equal to 1 to n small mi delta xi, where small mi is equal to infimum of alpha dash of x, where x lies between xi minus 1 and xi, true for all I between 1 and n. Now using the mean value theorem for alpha is now monotonically increasing and alpha dash belongs to R of R, so it is again differentiable. So using now mean value theorem for alpha, so using mean value theorem for alpha, for each I 1 less than or equal to I less than or equal to n, we can find in the interval, that is xi minus 1 and xi, we can find some ti such that, so I am applying for alpha, so it is alpha of xi minus alpha of xi minus 1, so which is equal to alpha dash of ti into xi minus 1. Now if you observe, this is nothing but delta alpha I, which is equal to alpha dash of ti into, this is nothing but delta xi. delta xi. Now for any si belongs to xi minus 1 comma xi interval, closed interval xi minus comma xi, summation I is equal to 1 to n modulus of alpha dash of si minus alpha dash of the ti is into delta xi. Now observe this alpha dash of si is always so see, si is in between xi minus 1 and xi, and mi is maximum supremum of alpha dash in this interval. So this must be less than or equal to alpha dash of si, and which must be greater than or equal to small mi. Therefore similarly it is true for alpha dash of ti. It is true for all i between 1 and n. Therefore we can say this one is now less than or equal to summation it is capital Mi minus small mi into delta xi. I varies from 1 to n. Now which is equal to summation. So it is capital Mi delta xi minus small mi delta xi. So we shall just distribute the summation. So minus, it is summation small mi delta xi, I is equal to 1 to n, I is equal to 1 to n. If you observe, this is nothing but up alpha dash, this is nothing but lp alpha dash. So which is nothing but alpha dash minus lp alpha dash. By Riemann criteria we have this one is less than alpha, less than epsilon, therefore this one is less than epsilon. So we got this one is less than epsilon, so let's take it as 1. Now let m be the supremum of modulus of f of x in surface bounded this exists on closed interval a comma b. Now consider modulus of summation I is equal to 1 to n f of si delta alpha I minus summation I is equal to 1 to n f of si into alpha dash of si into delta xi. Now it is modulus. Now taking common summation ending and taking this modulus inside, we get it is less than or equal to, so to common summation, that is I is equal to 1 to n, so modulus of, so this one is less than or equal to into, now again f of si is again common, so again taking this f of s outside, so it is f of si into here it is delta xi. Now delta alpha I, so we have delta alpha I is equal to alpha dash of ti into delta xi, so just substituting, that is alpha dash of ti into delta xi minus here it is alpha dash of si into delta xi. Now which is less than, now f is m is the supremum of f of x, so this f of si is now less than or equal to m, so it is m into summation I is equal to 1 to n. So we have alpha dash of ti and delta xi is common, so it is minus alpha dash of si modulus of alpha dash of ti minus alpha dash of si into delta xi, which is less than m into, now we got this one is less than epsilon, therefore this one is less than m into epsilon. This is true for all si belongs to xi minus 1 comma xi, xi minus 1 comma xi. Now using this, that is, we have modulus of this one minus this one is less than m into epsilon. So therefore using this expression, that is, this one is, we got it is less than m into epsilon. So using this expression, summation I is equal to 1 to n f of si into delta alpha I is less than summation I is equal to 1 to n f of si alpha dash of si into delta xi plus m into epsilon. And now if you observe, this one is less than or equal to up f alpha dash plus m epsilon. Now observe, this is the expression of L with respect to up f alpha dash. F alpha dash, by considering f alpha dash as a function, so it is f alpha dash of x, but f of x into alpha dash of x. Okay, now similarly considering in another way, that is summation I is equal to 1 to n f of si alpha dash of si delta xi. Now using this same expression, once again we are considering this. So it is less than summation I is equal to 1 to n f of si plus m into epsilon. So again, this one is delta si into f of si into delta alpha I plus m into epsilon. So again, this is nothing but less than or equal to up f alpha plus m into epsilon So it's again mistake. Okay, correct, it is UPF alpha. So, and it is true for like in Si belongs to xi minus 1 comma xi. Now that's we have in this. Now observe, this one is now with respect to up f alpha, and it is with respect to up f alpha dash. So combining these two expression, we get modulus of up f alpha minus up f alpha dash is less than or equal to m into epsilon. Now now observe this. We consider this expression with respect to one partition that we mentioned in the beginning, is P. So this is holds for every partition P. Therefore, because using Riemann criterion, therefore this expression holds for every refinement of P. Now taking infimum of up f alpha and up f alpha dash as P varies over all refinement of my original partition P. We get so integration A to B. So it is upper Riemann integral minus that upper Riemann integral f alpha dash dx modulus is less than or equal to m into epsilon for all epsilon greater than 0. Now okay, not this. See, I'm taking infimum of these two. So see, usually whenever we take infimum of UPF alpha, we are varying P over the P is the partition over the considered closed interval. But in the case I am taking the refinement of P, so this says it is enough to take such it is enough to vary the P over the refinement of P. So justify this step. So take it as an exercise, that is if f is bounded real valued function on closed interval and alpha is monotonically increasing, and P star is the partition of a closed interval a comma b, let A is equal to set of all UPF alpha, where P is a partition of closed interval a comma b, and B is equal to set of all U P dash F alpha such that P dash is a refinement of P star. Then prove that infimum of A is equal to infimum of B. That prove that infimum of A is equal to infimum of B, and supremum of A is equal to supremum of B. Take it as an exercise. So say here P star is a fixed partition of closed interval a comma b. Here I am taking UPF such that P varies over all the partitions of closed interval. But here I am taking those partitions of closed interval a comma b which are the refinement of P star. So then infimum is same and supremum is same. So using this we get as we vary this P over the refinement of my original P, and this P over the refinement of my original P, we get this. So this implies, since epsilon greater than 0 is arbitrary, we get integration A to B bar f d alpha, that is upper Riemann integral f d alpha is equal to upper Riemann integral f alpha dash dx, f alpha dash dx. Similarly we can prove lower Riemann integral a to b f d alpha is equal to lower Riemann integration a to b f alpha dash dx. Now suppose if f belongs to R of alpha on closed interval a comma b, then these two are equal, which implies these two are equal. That is implies f alpha dash belongs to R on closed interval a comma b. Suppose f alpha dash belongs to R on closed interval a comma b, these two are equal, implies these two are equal, that is f belongs to R of alpha on a comma b. So moreover we write integration a to b f d alpha is equal to whenever these two are equal, that is integration a to b f alpha dash dx, or it is nothing but integration a to b f of x alpha dash of x dx. Hence the theorem. So now so let's proceed. So the next theorem, that is it's also known as change of variable, which we have used several times in our lower classes. That is theorem. It's also known as change of variable. It's also known as change of variable. So it says, suppose phi is a strictly increasing continuous function that maps an interval That maps an interval. Okay. That maps an interval, closed interval capital A comma B onto small closed interval small a comma b. Suppose alpha is monotonically increasing on closed closed interval small a comma b, and f belongs to R of alpha, that is f is Riemann still J's integral on closed interval small a comma b. Define beta and g on closed interval capital A comma b by beta of y is equal to alpha of phi of y, and g of y is equal to f of phi of y. Then g belongs to R of beta on closed interval capital A comma b, and in this case we write integration a to b g d beta is equal to integration a to b f d alpha. So we shall prove this theorem. So given that my phi is strictly increasing continuous function, so it follows that, phi inverse exists and it is continuous on open interval a comma small a closed interval a comma b onto closed interval capital A comma b. Hence for the partition p is equal to x0 x1 so on to xn of closed interval small a comma b. This corresponding partition. This is a corresponding partition q is equal to y0 y1 so on to yn of closed interval capital A comma b, such that xi is equal to phi of yi for all I between 0 and n. That is for each xi. So my phi function is from a closed interval capital A comma b to closed interval small a comma b. So for each xi I am considering one yi. We get one yi. Okay, now since given f belongs to R of alpha, that is f is Riemann still J's integral on a closed interval a comma b. So by using Riemann criterion, that is for given epsilon greater than 0, there exists a partition p is equal to say x0 x1 so on up to xn of closed interval small a comma b, such that upf alpha minus lpf alpha is less than epsilon. Let's name this as star. Now since for any partitions a corresponding partition q exists, therefore for this partition let's take a partition q that is same as above, that is y0 y1 so on up to yn of closed interval a comma b, such that yi as phi of yi is equal to xi. This is true for all I between 1 and n. Xi is nothing but phi of I. Now note that okay, so say this is the partition AB, and this is the this is the closed interval a comma b, and this is the closed interval capital A comma b. Say here I am partitioned as x1 x2 similarly we get y0, y1, y2 and so on. So phi is a mapping from, phi is a mapping from, sorry, so this has to be there like this. So phi is a mapping from closed interval capital A comma B to small a comma b of a closed interval. Therefore we are restricting to a small sub interval xi yi minus 1 to yi minus 1 comma yi to xi minus 1 comma xi. Now it's a bijective function for each I between 1 and n. Therefore f of x, okay, I think wait a second. Okay, so consider the set f of x, xi minus 1 less than or equal to x less than or equal to xi, and consider the set of all g of y such that yi minus 1 less than or equal to y less than or equal to yi for each I between 1 and n. So we have xi is nothing but phi of yi. Therefore f of xi is nothing but f of phi of yi, and this is nothing but f of phi of yi is nothing but g of yi. Therefore these two sets must be equal. Therefore these two sets must be equal. Therefore if I take mi is equal to supremum of f of x, where x lies between xi minus 1 and xi, and supremum of g of y, where y lies between yi minus 1 and yi, say this is equal to mi star, then these two must be equal. Similarly, small mi is equal to infimum of f of x, where x lies between xi minus 1 and xi, also equal to infimum of g of y, where y lies between yi minus 1 and yi, say small mi star, must be equal, and this is true for all I between 1 and n. Now consider u, one second, consider u of q g beta, that is we are finding the sum of areas of rectangles under the curve G with respect to the partition Q and with respect to the Riemann-Stieltjes integral, and beta is the monotonically increasing curve, because phi is we have beta of y is nothing but alpha of phi of y. Now alpha is since alpha is monotonically increasing and phi is monotonically increasing, beta is also monotonically increasing. So we are considering u of q comma b g comma beta. So it is nothing but summation I is equal to 1 to n. It is capital Mi star into delta beta I. So which is nothing but summation I is equal to 1 to n mi, because mi star is also equal to mi into delta beta I is nothing but beta of yi minus beta of yi minus 1, which is again equal to summation I is equal to 1 to n capital Mi into beta of yi is nothing but alpha of phi of yi, alpha of phi of yi minus alpha of phi of yi, which is also equal to, which is again equal to summation I is equal to 1 to n capital Mi into now alpha of phi of yi is nothing but alpha of xi minus again alpha of yi is correct. Alpha of phi of yi is correct. xi minus, I made a mistake. Yi minus 1, it's xi minus 1. Correct. Okay. Now which is equal to summation I is equal to 1 to n capital Mi into delta alpha I, and what is this? It is nothing but UPF alpha. Similarly we get UQG beta is equal to UPF alpha. Therefore similarly we get LQG beta is equal to LPF alpha. Therefore UQG beta minus LPF alpha is equal to UPF alpha minus LPF alpha. Now which is less than epsilon using my Riemann criteria for integrability. Therefore this difference is less than epsilon, hence my it is LQG beta. Okay, UQG beta minus LQG beta is less than epsilon. Therefore my G belongs to R of beta on closed interval capital A comma B. Moreover we have LQG beta is less than or equal to integration A to B G D beta, which is less than or equal to UQG beta. Now again this implies, this is nothing but LPF alpha, which is less than or equal to integration capital A to capital B G D beta, which is less than or equal to UPF alpha. Now we also have since f belongs to R of alpha, LP also we have LPF alpha is less than or equal to integration A to B FD alpha, which is less than or equal to UPF alpha. Therefore their difference, that is modulus of integration capital A to B GD beta minus integration A to B FD alpha is less than or equal to UPF alpha minus LPF alpha, which is less than epsilon. Since epsilon greater than 0 is arbitrary, we get integration A to B capital A to B GD beta is equal to integration A to B FD alpha. Hence the theorem. So note that if we have in the above theorem, if we take alpha of x is equal to x, then we get beta is nothing but beta of we have beta is equal to beta of y is equal to alpha of phi of y, and this is nothing but, since alpha of x is equal to x, we have it is phi of y. Therefore we have beta is equal to phi. Therefore we get integration A to B f of x dx is equal to integration capital A to B f of, it is phi of x phi dash of y, in terms of y, phi dash of y dy if phi dash belongs to R on closed interval a comma b. In the above we had it for alpha dash, but we get it if whenever phi of alpha of x is equal to x, we get the condition for phi, and moreover integration a to b f d x, it's equal to integration a to b, capital A to b, that is g d beta, which is nothing but integration a to b g d beta, which is f of phi of y into d of phi of y, and which is equal to integration a to b f of phi of y into phi dash of y into dy. Hence this result. Thank you.